our current slide. We're at the top of page 298, finding area by the limit definitions. Okay. Uh-oh, I think I went past it. Nope, didn't pass it yet. I'll get there in a few hours. Okay, I think that's where we're starting. Okay, can y'all see the PowerPoint? Okay, good deal. Let me get it blown up a little bit here. Okay, we're recording. Has any new person come into the class yet? Did y'all see anyone trying to make his or her way in? Because you see, once I get everything open here, I don't see the entry anymore. I'm going to do it one more time just to look. It says I should have 14 students here. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So evidently one person showed up and then disappeared. Clever, but not going to do them any good, but you got counted present when you are not here now, but that's your problem. Okay. Any questions from anybody? All right. Now, I can't remember if it started in this class or not. It may have, that you wanted me to start using the whiteboard rather than showing you things on the camera. Was that this class? Say again?
Yes.
It was, okay. Well, just about every other class has agreed that's a better way to go, so I'm going to be trying to do that. I'll use PowerPoint when I can, but when I can't, I'll go to the whiteboard. And my writing's terrible, but if you weren't here last time, you can blame the rest of them. Okay. So, if there's no questions, are there any questions? I do appreciate several of you have been sending in materials. I haven't been able to set up my grade book yet because, as far as I can tell, they're still letting people in class, and that's maybe not this class, but other classes, and that's really difficult to handle because they've missed so many classes, but I guess they're doing everything they can to get summer students here. So, as soon as I get the grade book set up, then I'll be able to start entering things on as far as grades and stuff. But I'm just keeping roll on the piece of paper, and it's really crowded to try to put scores on there as well. Once I get the grade book set up, it'll be a lot easier. So, any questions, any issues, any complaints, rejoicings, anything?
I had a question.
Okay, wait, somebody's in the waiting room. Let me... Oh, Daniel must have had to go out and come back. Okay, yes, somebody said something. 2 people. Either one.
Yes. You go first.
Okay.
Do you know about when our first test will be?
Okay, hold on a minute. I just had your manual show up. Let me mark them on the roll. Okay? Now, it also says my internet connection is unstable, and that may be why a few people were sounding garbled, but I did hear someone say, do I have any idea when the first test will be? Well, since this is only our, third class? Yeah, I believe it's our 3rd class. We're not there yet, but we're going to be there when we finish section, let me see. We got a ways to go is what the point here is. Okay, we definitely are going to finish 5.5. And we're in 5.2 now, so we've got a ways to go, but we're going to try to pick up steam a little bit. Okay, we're going to try to do 5.6 as well. That's an important section. Okay. Okay. Oh, 5.7, we got to do 5.7. Yuck. And it may be Yuck. We got to do 5.8 as well. I was going to say we might be able to skip that one, but that's pretty important too. Hyperbolic functions 5.9, we're definitely going to skip that one. Okay, I'll talk a little about it, but that's about all. Okay, and then that's it. So we got to go through 5.8, so we got a ways to go. I think that was a way that Amina was trying to get me to move along here, I believe, whatever. Okay.
No.
Nah, okay. All right. There was another question I thought.
Yes, sir. I was wondering again, how do you want us to submit any homework assignments?
Okay. You can either, you got several choices. If you work it out, you can either scan it and send it to me as an attachment to an email or to a message on Blackboard. That's one way. Two ways, actually. Or if you don't have a scanner available, which a lot of people don't, you can take a picture with a smartphone. I think those are usually JPEG files, and you can attach that either to an email or to Blackboard. Okay, message on Blackboard. And I believe all that the dean actually wants is once a week. So you don't have to do one every class, and you don't have to send every homework assignment. Some of you are, that's perfectly fine. I especially want to see multiple ones if you're having trouble. If you're having trouble, please make some annotation on it. I can't get this one to work out or something like that. But if you're breezing through these things, just send me one or a couple or whatever you want. A single page is usually enough. Unless you're having problems, then sort of highlight where which of those are giving you difficulty. And then either in class or out of class, we'll try to address those. That's probably not quite all you were asking, but is that enough?
Yes, sir. That was exactly what I was asking.
Okay, good. All right. Any other questions? Great questions, by the way.
Did you still want us to send you the syllabus?
Okay, that one page from the syllabus, yeah, that was the first week's assignment. You didn't have to do any problems then, just send that. But if you sent something else instead, technically I'm supposed to have it, but I can live without it. If you sent me something else for that first week, I'm perfectly happy with that. Because at the end of the term, they all get trashed anyway, that page from the syllabus. So it's not going to be a huge loss if I don't get it. But I don't want you coming up and say, well, I didn't know this. He didn't tell us, and it was in the syllabus. You see, if I have that, then I hold it up and say, yeah, you said you saw it, read the syllabus. Okay, so you see, it's protecting me from your gripes. Say that again?
I got a question.
Okay, what is it?
All right. I remember at the beginning of this semester, this term, you told us that it was two forms of the book, and I think I got the older form of the book, and the chapters are different.
Okay.
Did you want me to go ahead and get the updated version of the book?
Okay. Okay. Do you have I believe it's 11th edition of just Calculus by Larson and Edwards? Yeah. Is that what you got?
Yes, sir.
Okay. The material in here is the same. Like you said, it's just mixed up in different chapters. For instance, their chapter 5 in that book, if my memory's right, was just stressing with transcendental functions. Okay?
Yeah.
I think their chapter 4, no, maybe, I don't remember which, but one of their adjacent chapters was the integration chapter. Now, when we get so far in the integration chapter, your book is going to lose it. Then you go to your chapter 5 and pick up those that deal with logarithms and exponential functions, and I believe probably inverse trig functions. When we get to that section in this chapter, you'll have to go to your chapter 5 and find those. But you'll see they're almost identical. It's just where they're located. It's a shell game. They just moved them around some and got credit for writing a different book. So I don't know how they do things. So as long as you can navigate your way through that book and cover the same stuff, perfectly fine. most of the exercises, if they're not exactly the same, they're going to be similar. So now, others of you coming from other campuses, hey, if you used a different calculus book, I know you got a chapter in there on integration or antiderivatives or something like that, and you can use those chapters. You don't have to have this particular one. For the page numbers, chapter sections, and stuff like that to make sense, yeah, it's helpful, but if you have what I'll try to do from now on, well, I think I do it already. When I say the chapter number, I say what the chapter's about. When I say the section number, I say what the section's about. Find that in your book, you'll be okay. Unless that's just too confusing to you, and then go make Cengage happy and buy another book, okay? Or share with somebody. Or use Cengage Unlimited. If you've already in another course with one, you got it for free, kind of. Any other questions? Did that answer yours, Houston?
Yes, sir.
Okay. Did Daniel Thaxton say something? Okay. I thought Daniel's light came on, but then I couldn't hear anything. Daniel, did you say something? No?
No, sir.
Second?
No, sir.
No, okay. All right, any other questions, issues, concerns? All right, then, I guess without further ado, we'll continue. Chapter 5, Integration, Section 5.2, Area, and we're in the section entitled Finding Area by the Limit Definition, which is exactly what this says. Now, I have a question for you. Is part of this title here blocked out by a rectangle that's now fading out? Okay, wait. Kyle must have gotten sick and left. Sick of me and left. Oh, something. He's back, though. Okay, I hope so anyway. All right. And let me say one more thing. I don't know if it's Zoom. I don't know if it's internet service providers. I don't know if it's what the issue is, but yesterday in one class, I started the class a lot like this one, getting people on the roll and stuff like this, and then all of a sudden they couldn't hear me and I couldn't hear them. I took Zoom down, I did everything I could think of, finally had to shut the entire computer down, bring it back up from scratch, and that meant all the PowerPoints and Screencast-O-Matic and everything else, and finally brought it back up, and then everybody was fine. So occasionally there are issues. I don't know who the issue is with. It may be your internet signal, your Wi-Fi router. It could be mine. I know every now and then I'll get a little thing saying my internet signal is weak. Sorry about that, but we have to live through this, so try to hang with it. All right, any questions? All right, finding area. I didn't hear an answer on whether this block is blocking your view, but I didn't get an answer. Let's move on. All right, I can't get it to advance. I have to click on it once and then it'll advance. Okay. Consider a plane region. Okay, here's your XY plane. Now, is this block in the middle blocking some of that? Do you see a rectangle right here in the middle? Yes or no?
Yes.
Yes. I can't do a thing with that. I've tried and tried and tried. I'm going to try one more thing here, but I don't think it's going to work because I believe I've tried it before. What that is, yeah, it's going to be in the same place. I can't do a thing about it. It's something that I guess Zoom does, and I can't do a thing with it. It fades away, and then you can see. So here's an XY plane. You can see the Y-axis, or at least part of it. Somewhere under here is the X-axis. I can see it, but I guess you can't. Now you're beginning to see it, right? Here is some function in the XY plane. F is some function of X, and F of X is your Y. You know that from earlier. Now we're only going to consider this function in between A down here, you can't see it yet. I'll wait until the block fades away. Well, at some point I hopefully will. Okay, there, it's beginning to fade away. There's my pointer. It's going from A, and A is just to the right of 0, to B, and B is further along. And now it's blocking it again. Now what that is, that's where zoom window comes up when you're coming into the classroom, okay? And Zoom is trying to block that. It says, please do not move this window away from the shared application. Well, I have no way of moving it. I've tried and I've tried and I've tried. Nothing moves it, okay? It just sits there. And yet they tell us to move it. Never mind. Okay, my problem. So here is a plane region in the XY plane, bounded above by the graph of a non-negative continuous function y is equal to f of x. Now sure, this function f of x goes negative over here to the left. I'll wait until the rectangle gets out of the way. Sorry about that. But we're not considering this part where it's going negative. We're only considering between a and b, and that f is always positive there. So we're considering just this plane region bounded above by the graph of a non-negative continuous function y is equal to f of x. Now don't sweat it. In the future, we're going to have negative functions. We'll have all sorts of things. Don't sweat that. The region is bounded below by the x-axis, and it's fading out now, and hopefully you'll see it in just a second. There's the x-axis. That's the region we're interested in, this little pink region right in there, okay? It's bounded on the left and the right by the vertical lines. I'll wait a moment, let this fade away. I don't know why it's not going to fade away faster. There's nothing there, and it says, please move this window away from the shared application. So I wish I knew how to handle that. I don't. Here's the line x equal a, vertical line x equal a. Here's the vertical line x equal b. So that is the region we're interested in, that little pink region right below the rectangle, which should not be there, okay? To approximate the area of that region, that's going to be a little tough because it's a curved region all along there. Begin by subdividing the interval a to b, and remember the bracket here means you include the endpoints, a to b, so you're going to approximate this area from a to b under the curve f here into n subintervals, okay? So what we're going to do to determine that is do b minus a, b minus a, divide that by n, and that's your delta x. That's how big of a region that is, okay? Now, they show here a little rectangle. That rectangle has its left-hand endpoint here on the curve, and the right-hand endpoint is vertical from that. But it also shows another little rectangle down here whose right-hand endpoint, right-hand side of that rectangle intersects the curve, okay? Now, the upper rectangle is going to overestimate the area under the curve. The lower rectangle, this one down here, is going to underestimate the area of that region in delta x, okay? So, but that's what your delta x is. It's your distance between b and a, b minus a, divided by n. That's how many subintervals you have, okay? Now, the area of this rectangle, if you're using the larger rectangle, is f at this endpoint. If you're using the shorter rectangle, it's f at this endpoint, okay? That's what determines the height of the rectangle. The width you already know is delta x, and the delta x is b minus a over n. So there is how we're going to approximate the area under the curve. And hopefully from your Cal 1, you got a clue of what's coming. We start with any n that we want to, get a larger and larger n. That's going to make a smaller and smaller delta x. You're going to have more and more little rectangles here, and each one of those is going to approximate an area either above or below the curve. But the smaller you get, the closer the approximation is. Of course, you got a lot more rectangles, but we can live with that. And that's how we're going to estimate the area under the curve. I jumped ahead there. Let's move on. The endpoints of those intervals are, okay, the first endpoint is going to be A, okay, because that's the left-hand endpoint, okay. Now, to write that a little more complicatedly, we'll say A plus 0 times delta x, because you haven't moved from A. The next endpoint is going to be A plus 1 times delta x, and we're going to call that x1. That's going to be that endpoint. The next endpoint is going to be A plus 2 delta x. We'll call that x sub 2. All the way up to the last endpoint is going to be A plus n delta x. Now remember, n delta x was b minus a over n. So when you multiply the n times b minus a over n, the n's go out. That gives you b minus a plus a. That gives you b. So sure enough, that's it. While it's faded out, because f is continuous, remember that was a requirement, the extreme value theorem guarantees the existence of a minimum and a maximum of the value f of x on each of those tiny little subintervals. So let's call f sub little n I mi the minimum value of f of x on that ith subinterval, and f of capital M sub I the maximum value of f on that ith subinterval. That's what the sub I tells you. That's which subinterval you're in. Now, I'm going to back up one slide, and let's look at this rectangle again. This is your capital M sub I, because that is the larger value. This is the least value, so that's your f sub little m sub I. So don't say one's right and one's left. One's max, the capital M, and one's min. It's not that the m sub I, those are values of x. Capital M sub I actually turns out being less than little m sub I. We're talking about the m's there. The function, though, at capital M sub I is greater than the function value at little m sub I. Okay? That's what the capitals are. They're doing them on the x variable, but you're talking about them capitalizing the maximum value on the y. Okay? It's a little bizarre the way they do it, but it's okay. We can handle bizarre, right? Okay. Next, we're going to define the inscribed rectangle. That's the rectangle. Oh, wait. Let me go back to that again. What if we had, and let's just, if you'll follow my cursor here, let's say that next delta x goes over to here, approximately, right? Then it would go up to here, approximately. Now the minimum value is going to be right down here, the maximum value here. So it doesn't have to be an endpoint, okay? It could be the lower dip, because what it is the value in between x sub, x of n and x of n plus 1, some value in there, some x value here that gives you the least value for f and one that gives you the greater value for f. That's what we're talking about with the capitals and lowercase m's. Okay, so next we're going to define an inscribed rectangle that lies inside that ith subregion, and a circumscribed rectangle that extends outside the ith region. Now that's what we saw before, and that was right on the endpoints. I can't get it to advance. I hit the wrong button, sorry. Okay, whoops. No, I've gone too far. Have I? Yeah, I've gone too far. My finger went crazy. How did I get way up there? Okay. Here is the inscribed rectangle, the one that goes to f sub little mi. here's the circumscribed rectangle, the ones that goes at capital I. If you were down here, the one that went here would be completely under the curve. The one here would be completely over the curve, outside the curve. Okay? So that's what we mean by the inscribed and the circumscribed rectangles. Okay? The height of the ith inscribed rectangle is f m sub I, because this is the inscribed, little m sub I. The height of the ith circumscribed rectangle, whether this m is greater or less than that one, it doesn't matter. So it's not the x value, it's the f value, okay? And that's going to be the one at the circumscribed. For each I, I'll wait till the box fades out a little bit, the area, that's what that starts to say, the area of the inscribed rectangle is less than or equal to the area of the circumscribed rectangle, guaranteed, okay? So the area of the inscribed rectangle is your f sub little m sub I delta x, and your that's always guaranteed to be less than or equal to f sub capital M sub I times delta x. Area is the height times the width, height times the width. And this is equal to the area of the circumscribed rectangle, the one at the right-hand side. All right. They're beating this to death, aren't they? Okay? Now, the sum of the areas of those inscribed rectangles, the little ones, is called the lower sum, and the sum of the areas of the circumscribed rectangles, the larger ones, are called the upper sum. So your area under the curve is going to be something in between the lower sum and upper sum. So the lower sum is going to be little s sub n. Now this will make sense. It's the sum that's the smallest, okay? And the capital S is the upper sum of all those rectangles. Your f sub little m sub I times delta x, the summation of all those rectangles from I equal 1 to n, and the capital S sub n, the upper sum. As soon as this fades out, I'll do it for you. I wish I could get rid of it, but I can't. That's your summation from I equal 1 to of f sub capital I sub m delta x. That gives you all those sums over that rectangle. Okay, so here is that first curve that we saw split up. From this figure, you can see that the lower sum, s sub n, little s sub n, is less than or equal to the upper sum. Here's the lower sum here. The blue rectangles down here, they don't quite match up. Every one has a little triangle. See this one here? Very, very close, but there's a little bit of pink there and bigger here, here, and there. Okay? But this one, the circumscribed rectangle, they all have a little bit of their areas, okay, greater than the area under the curve. So the actual area under the curve is in between the little s sub n and capital S sub n. Okay, that's what this is saying. The actual area of the region lies in between those two sums. Make sense? Yes, of course. Any questions? Okay. Here's example 4. This is on your page, my page 299, whatever book you have. See if you can find one like it. It says, find the upper and lower sums of the region bounded by the graph of f of x is equal to x squared and the x-axis between x equals 0 and x equals 2. Now, without drawing anything, I'm going to let them draw it. Let's picture what this is. What does that shape become? F of x equals x squared. What does that graph as? Help me, sir. A parabola. What's its minimum value? Where? At x equal 0, of course. Past 0, it's going up. To the right of 0, it's going up. Minimum value at 0. We're starting at that minimum value. Okay? So in this region, between x equals 0 and 2, the maximum value is going to be at x equals 2. and that is going to be a curve, a parabola, starts at 0 and then makes its way up to 4 because of x equal 2, the value is at 4. So let's see if they drew it correctly. Oh, they don't show it yet. So it says to begin with, partition the interval between 0 and 2, there's your 0, there's your 2, into n subintervals, and that is going to make each subinterval, the width of that, delta x, b minus a, which is 2 minus 0 over n. Now, they haven't told you what n is yet. So that's where we're going to begin. Okay? Now, and there we have it. Delta x is equal to 2 divided by n. All right. There it is. They just did it too. 2 divided by n. Now, in this figure, the left-hand figure here, shows the endpoints of the subintervals in several inscribed on the left, circumscribed rectangles on the right. Because this is a strictly increasing function, if you go with the left-hand endpoint, you are going to have the inscribed rectangle. The right-hand endpoint of those rectangles will give you the circumscribed rectangles. A function like we saw at the beginning that goes up and down, that can vary. But this is strictly increasing. The left hand is going to be the inscribed, and the right hand is going to be the circumscribed. Okay? So they happen to choose their n to be 4, it appears. 5 actually. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay? So their n was 5. So what is their delta x? 2 divided by 5, 0.4. So this first point here is 0.4, 0.8. Wait, I'm going to say, 0.4, 0.8. My cursor went away. There it is. 1.2, 1.6, and 2. Okay? Those are the values of the x values of those endpoints. Okay? Now, what was the question here? Find the upper and lower sums for the region bounded by the graph of that and the x-axis between that. Now, they didn't give you an n. They chose 5, but you're not limited to that, I don't think. So let's move on. Because alpha is increasing, what I just said on that interval from 0 to 2, the minimum value is always going to be on the left endpoint and the maximum value on the right endpoint. So let's write down what those endpoints are. The first one on the left, that's just going to be 0. Okay, now they say 0 plus I minus 1 over 2 times 2 divided by n. This I minus 1 is your, which endpoint you're talking about, the one to the left. So it's I minus 1. So the first endpoint will be to the left, so that'll be at 0. So that's going to be a 0, okay? So 0 plus 2 plus 0 times 2 over n is just 0, okay? But the second one will not be. When I is equal to 2, then this will be 2 over n. When I is equal to 3, so on. So this gives you that formula. 2 times I minus 1, just bring this up and put it on the right-hand side, 2 times I minus 1 over n. The right endpoint is going to be 2 at 0 plus I times 2 over n, which is going to be 2i over n. Okay? This is 2 times I minus 1 over n. This is 2i over n. This is always 1 to the left of this one. Right and left hand. Okay, so those are expressions for your left and right hand endpoints. Okay, let's move on. Using the left endpoint, sorry about that, this stupid box is in the way. Okay, using the left endpoints, the lower sum is then the summation of all those values. It's f of m sub I, which is, remember, x squared, okay, times the delta x, but the delta x we've already done was 2 over n. That was your delta x, Okay? So this is equal to, as soon as it fades out, the summation for I equal 1 to n of f of this value, your little m sub I, 2 times I minus 1 over n times your delta x, which is 2 over n. If your right-hand endpoint, it's going to be just like this, only this is the expression that you put inside the f function. Okay? So, now, what they're doing here, remember your function, f. F is x squared. So whatever is on the inside, you're squaring it. Okay? So this is the summation of 2 times I minus 1 over n squared. So that means the 2 is going to be squared, the I minus 1 is going to be squared, the n is going to be squared, times 2 over n. Well, you had 2 squared from here times another 2, that's going to be 8 always, and this is always going to be n cubed in the denominator. So say 8 over n cubed can go on the outside for certain, okay? Okay? Then all you have left is I minus 1 squared. Okay, so let's see how that works. There's your 8 over n cubed. You could pull it on the outside because n's a constant in this problem. It's whatever you choose your number of intervals to be. And then when you square I minus 1 squared, that's I squared minus 2I plus 1. So that's where you get I squared minus 2I plus 1. Time out a moment here. If any of you have dealt a lot with complex variables, do not confuse this I, which is your counter right here, with the I, which is square root of negative 1. We use the same letter for them a lot of times. Always I means square root of negative 1 when you're dealing with complex numbers, but quite often I is going to be a counter when you're talking about sigma notation. So don't get the two confused. This I is not the square root of negative 1. So don't even go there. Maybe I shouldn't have even said it. All right? But anyway, we can take this, pull this on the outside. Now, remember last time, what was the summation of I squared? Flip back a page or two. Okay? Summation of I squared on the box on page 295 in this text, that was n times n plus 1 times 2n plus 1 divided by 6. And then you can move your summation, pull this on the outside. You can do a summation of this, which we just gave you the value there, minus 2 times the summation of I. Well, the summation of I from that same page is n times n plus 1 divided by 2. And then 1, the summation of 1 from I equal 1 to n is just n. Okay? 1 times n. Okay? So that's what they're going to do next. And here's what it is. Like I said, pull the 8 over n cubed to the outside. There's no I dependence there. This is only counting i's. It's not counting n. N's a fixed number. Pull it to the outside. Then break this remaining sum down into the sum of I squared minus 2 times the sum of I plus the sum of 1. Okay? And like I've already said, we know what those values are. The 8 over n cubed, that's coming back in a minute, that's on the outside. This summation here, it's coming back soon to a station near you. Okay, please get out of the way. That is blocking your view, isn't it? I can't do a thing with that
Yes.
ridiculous rectangle. But when it fades out, you can see it, right? So you can see that now, right? Okay, so this summation is n times n plus 1 times 2n plus 1 over 6 before it faded out, minus 2 times, and the summation of I is n times n plus 1 over 2, and then the summation of 1 from 1 to n is just n. It's n plus n, 1 plus 1 plus 1 plus 1 plus 1 n times. So that's just n. Okay. Now, hopefully, yeah. Now, they skipped a bunch of steps, obviously. Okay? A whole bunch of steps. I don't know what that noise meant. I thought maybe someone else was coming in the class, but I don't see them. You let me know if you see someone trying to get in. Okay. Do I need to go to the whiteboard and work out how they go from this step to that step? Or can you do the math and figure it out on your own?
Can you go to the whiteboard?
Okay, let's do it. All right. Y'all help me remember what it is. Okay. So let's go to the whiteboard. All right. Here we go. Let me see if I can write down what they had. 8. You would have thought I'd have gotten better at this after teaching 4 more classes in between this. Over n squared. That was it, wasn't it? Okay. No, n cubed. 8 over n cubed. I forgot. That was, okay. Watch this magic here. That became a 3. Wow. All right. That's times. Okay. The first one is n times, that's, let me erase that. I lifted my finger, but it didn't lift, well, there. It erases part of it. That's fine. Okay, go back to drawing. Okay. N times n plus 1 times 2n plus 1, wasn't it? Yep, 2n plus 1. Do I memorize these things? No, that's not worth it. Look them up if you know. That's supposed to be a 2. N
times n.
Okay, it's n times n plus 1 times 2n plus 1. You write it down on your paper and you write it neater than me. If you write it this sloppily, you lose a bunch of points, okay? All that is divided by 6. I would type these, but they don't allow you to, it just won't work, okay? And then we had a minus 2. And then the summation of I was n times n minus 1, or 10 plus 1, wasn't it? I'm doing this from memory, so, and my memory's not good. I'm old and decrepit. Yeah. N times n plus 1 over 2. That didn't write too well, but it did all right. Plus n.
Are you able to see when, like, I write on the board? Because maybe I can write more,
okay.
I guess, neat.
I should have asked that. Do one of you have a stylus?
I do.
You do. I had one in another class. If you can do this, try it.
Okay.
Now, the student in my other class had to have like 2 computers and multiple screens. There you go. Yes. So you want me to erase mine? Let me erase all and let you get started again, okay? Are you okay?
Okay.
Okay, let me erase, because otherwise you're going to get in the box there. Okay. All right, start over. Thank you for volunteering. I wish my old computer, I wouldn't need this whiteboard. It was a tablet computer, and that's what I did all the time. But that computer died, and they didn't have any more and gave me a nice, fancy HP that won't do anything that I need it to do. Okay. All right, you writing yet?
What's the problem?
Oh, okay. Yeah, I'll call it out to you. 8 over n cubed, just like you had. Okay, and then open bracket. Okay, now, in the numerator of the first term, it starts with an n, just an n, times, with open parentheses, n plus 1, n plus 1, n times n plus 1. Can you erase, or do I need to?
I'm trying to erase.
Okay, let me try. Let me do it. I know I can do that. Oh, look at that. Okay.
Okay.
I don't know who did it, you or me, but it doesn't matter. No, n times n plus 1. The first n is outside the parentheses, and then the next one's that. Okay, n times, open parentheses, n plus 1, close parentheses, times, open parentheses again, 2n plus 1. 2n plus 1, close parentheses. All that is over 6. Okay, next term. Minus 2 outside the... Oh, wait, don't close the bracket yet. Oh, I need to erase it, don't I? Oh, you did, didn't you? Okay. Now do a minus 2 on the same line as that. Yeah, minus 2. Now open another bracket. This is bizarre how they do the brackets, but it's okay.
What'd you say?
Open another bracket after the 2. You'll have 2 brackets open then. Yeah, right there. And do an n times n plus 1. So in other words, n, open parentheses, n plus 1, just like you did before. N times n plus 1. N outside the parentheses, n plus 1 in the parentheses. Okay? Sorry you don't have my book. Okay. N times n plus 1. Okay? And that's over 2. Those 2 terms are over 2. 2 factors are over 2. Okay? Then close that second bracket that you had that follows the 2. Close that one. Can you see my... Yeah, you got it. Okay, and then do a plus n at the end.
A plus what?
Plus n. That's all. Just a plus n. Okay. Now I'm having trouble reading because... Okay. Still have trouble reading, but it's okay. Now, close your big bracket at the right-hand end. That really should be a brace there. I misread it as a bracket, but it's a okay, got it. Okay. Now, what we're going to do now, first thing to note, the 2 here cancels out that 2. Can you see my eraser? Yeah, you got it. Excellent. Okay. Now let's combine terms. So let's go on and write down the 8 over n cubed again. Maybe make them a little bit smaller. 8 over n cubed. Okay. And then this time open a brace here. Not a bracket, a brace. Okay, anything will do. Good. Okay. Now, all right. I'm trying to figure out the easiest way to do this. One thing is every one of these terms, n, they all have an n in them. Here's an n down here. So let's take out those n's up here, one of them, and make this just an over n squared down there. Can you see my eraser when I move it like that?
Yeah.
Okay, make that okay, good. Now, open a brace here. Okay, now, we've taken out the n. Now, we have an n plus 1 times 2n plus 1. What's that? That's 2n squared, so write that down. Okay, let me think if what I just said was right. Yeah, I think it is. Okay, 2n squared, and then plus n plus 2n, so it'd be plus 3n. And then you have a plus 1. Okay, and that term is all over 6. Those 3 terms are all over 6. Okay, and this one we've already gotten rid of the 2's. We factored out an n, so you just have n plus, okay, you still got a minus sign here. So it's a minus n minus 1, and then you have a plus n. So that's just going to be a minus 1. Or you can write those if you wanted to. Do y'all see that? We factored out the n, got it out here, got rid of that one, and that gave us just an n plus 1, a minus n plus 1, which would be minus n minus 1, plus n. The minus n's go to 0, and that's just a minus 1. Okay? Now, put your equal sign here. Okay? Now, I'm going to do something else here. Since this has a denominator of 6, let's make this have a denominator of 6 too, except that it's 6 over 6 now. 1 is 6 over 6, so just erase this and make it minus 6 over 6. All right, good. Now, and that's all inside your big parentheses. So you need one more bracket outside this one, and yeah, you got it. Okay, good. Now, what happens here? 2n squared plus 3n plus 1 minus 6, that would be a minus 5 over 6. Okay, but wait, time out. Before you do that, notice that the 6 you can divide, because both of these have 6's in them, you can divide 2 into this, that would give you 3, 2 into that would give you 4. So past the equal sign here, change that to 4 over 3n squared. Okay, see what we did? We pulled out the 6 with the 8 and made that 4/3. Okay, now open up your parentheses. Okay, and that gives you 2n squared plus 3n minus 5. Now, how did they get... I must have done something wrong here. I thought it was legal for me to factor out an n out of every term, and they're sort of indicating it's not. But let me see. Let's just see. Okay, I made a dumb mistake somewhere and I can't see where it is. I think it came from factoring out that n. I must have done it too soon.
I can't hear what you're saying.
Oh, okay. They got a different answer from me, and I think the reason they did, when I factored this n out, I thought that was going to be legal at this step. Evidently, it wasn't, okay? I can't right now figure out why it's not, but it's not. That's the only thing I can see that creates a problem here. Can anyone see why this method didn't work? What they did, they went on and multiplied all three of these together, which is a pain in the neck, and they then multiplied these two together, which is not bad at all, and then this one, and they came up with a slightly different answer from me. But here's the point, okay? It really doesn't matter too much. I guess it does in some senses, but put your parentheses here. I think what we're going to wind up with is the same answer. Put your parentheses here. You see where I'm talking about? Close that out. Got it? Do you see what I'm saying? Close that. After the 5, put a parentheses. Okay, got it. Now, let's multiply through. this would be 8 over 3, 8n squared over 3n squared, right? Which is just 8/3. Okay, yeah, 8/3. Very good. Do it down there. Okay, 8 over 3. And this one gives you a plus 4 over n, because this has an n, that has an n squared, so that'd be plus 4 over n. So that's your next term, plus 4 over n. See? 4, plus 4 over n. Because the 3's would cancel out, and one of the n's cancels out and gives you 4 over n. Very good. 4 over n. And then you have a minus 20 over 3n squared. That's the last term. Minus 20 over 3n squared. Okay? And guess what, folks? As n goes to infinity, gets infinitely large, this term goes to 0, and that term goes to 0. You're left with 8/3. So however they did their math, you still come up with the same thing. The lower limit is 8 over 3. Okay? Now, doing the upper limit, let me go and erase the board. This listing of all the people here is just sort of getting in my way here. So I'm going to move it over here. Okay, and I'm going to erase the entire board here. Oh, I thought I was going to erase the entire. There we did. Okay. Now, if you do the capital S of n, that was, let's go back to the screen. Sorry. Let's go back. I think there's no reason for me to do it. Okay. New share, and we'll go to, for some reason it's going back where we've already been. Okay, and starting over. Goodness gracious. Okay. All right, there's where we were. Now this thing's in the way again. You can't see what I'm talking about, but Alea's in the way again. Okay. I'll move everything up top. Okay. So here's what we got for the little n. Okay. This is where we left off. The next slide takes us to this. 8 over 3 minus whatever else you got, the lower sum figures up to be, as n goes to infinity, it going to 8 over 3. Now using the right endpoints, the upper sum, that's capital S, that is f at the larger value, which will always be the right-hand value of your m, times delta x. And remember, the delta x is 2 over n. The capital M now is going to be, no reason, okay, it's 2i over n, okay? So f of 2i over n. Now you don't have the I minus 1, you just have 2i over n, okay? And f of that would be this thing squared. So that'd be 4i squared over n squared times 2i. So let's see what they do next. There it is. They squared this. F squares whatever's in parentheses here. So that's 2i over n squared times 2 over n. And that's 8 over n squared. That's 4 times 2 is 8. N squared times n is n cubed. You can pull that on the outside, and you're just left times the I squared. So that'd be 8 over n squared. And then what is the summation of I squared? They skipped a step here. Where's my cursor? They pulled this to the outside, 8 over n cubed, and you're left with summation from I is equal to 1 to n of I squared, which we already know to be this n times n plus 1 times 2n plus 1 over 6. Okay? Now, all right, here they do their magic again. Now, at this stage, I would say cancel 2 into 8, and you get 4. Cancel the same 2 into 6, you get 3. So that's where you get your 4/3 that we'll show on the next slide. Cancel this n out of the way, and that makes this an n squared. So you have a 4/3 n squared times the product of these two. Okay, that's what I'm going to do now. 4/3 n squared times, well, they left the n cubed in there. Let's go back and let's us figure what the product of these two are. We've already done it once. 2n squared plus 3n plus 1. Okay? I already factored out the n and got rid of that. So that's where they get 2n. They have cubed, but I factored one of the n's out already. 2n squared plus 3n plus 1. But I already made that an n squared. So there is your upper sum. Okay? And when you multiply that through, you get 8/3 because, there it is. 4 times 2 is 8. N cubed over n cubed is 1. So it's 8/3 plus, and this 3 cancels that 3. 4/n, because this n squared cancels 2 of those out, but you're still left with 1. And then you get a 4n/3n cubed. That would be 4/3n squared. And again, when n is going to infinity, that goes to 0 and that goes to 0. Again, you're left with 8/3. So guess what? The sum of those, both as n gets very, very large, meaning your intervals are getting very, very small, both of those sums are going to 8/3. That means the area under that curve was 8/3. Okay? Now, I jumped the gun on them here. And that's because they're waiting on a theorem to tell them that they can do this. Okay? So the next theorem shows that the equivalence of the limits as n approaches infinity. That's what I was doing, remember? Let n get very, very large, and anything with n in the denominator is going to 0. Of the upper and the lower sums is not mere coincidence. It's true for all functions that are continuous and non-negative on the closed interval from a to b. That's where we started. It always works. So the limits of the lower and upper sums, let f be a continuous non-negative function on the interval from a to b. The limits as n approaches infinity of both the lower and the upper sums exist, and they're equal to each other. So that's saying the limit as n goes to infinity of the little sum, the lower sum, is that thing with m being the value that gives you the minimum f, and that's the same as the limit as n goes to infinity of f of the capital M, which gives you the largest value of f, all multiplied by delta x, and that gives you the limit. Why they chose capital S? Oh, I see. I'm sorry. They're starting here, going here, saying this is the same as that. That's the magic, and that's this. So these are going to have the same limit. Oh, here comes Joy back. She must have had to leave, and she came back, but I already have her present. So where delta x is your b minus a over n, your f sub little m is the minimum value of anywhere on the subinterval. F sub capital N is the maximum value anywhere on the subinterval. That is going to be the case, as long as you have continuous, non-negative functions on the interval from a to b. So, I have to hit the screen again. And now, in theorem 5.3, the same limit is obtained for both the minimum value and the maximum value. So it follows from the squeeze theorem, way back in chapter 2, theorem 2.8, that the choice of x in the ith subinterval does not affect the limit. You can choose any x. It doesn't have to be the max. It doesn't have to be the min, because the max is going to be the highest, the min's the lowest, and if they all have the same limit, any x you choose in there is going to work. So here's theorem 2.8 again. squeeze theorem, if you have some function h of x, which is always less than or equal to f of x, but that f of x is always less than or equal to some g of x, for every x in the open interval containing some value c, except possibly at c itself, we're not worried about that, and if the limit as x approaches c of h is L, and the limit as x approaches c of g, the larger function, is also L, you have no way except the limit as x approaches c of f also has to be L. Because if h is approaching c, g is approaching c, I'm sorry, h is approaching L when x approaches c, and g is approaching L when x approaches c, and f is always in between the two, it's got to approach L too. They call it the squeeze. Sometimes they used to call it the sandwich theorem. Okay, if you're hungry, I guess you called it that. Okay. Now, that means that you are free to choose any arbitrary x value on the subinterval, as shown by the definition of the area of the region on the plane. So, here's that definition. Let f be continuous, remember that was required, non-negative on some interval a to b. There's your a, it's positive there, always positive up to b, so yep, it fits, it's continuous all in there. The area of the region bounded by the graph of f, the x-axis and the vertical lines x equal a and x equal b, okay? The area under there is the limit as n approaches infinity of the summation of I to n of f of any old c sub I you want to choose. It could be the center value, it could be the right-hand edge, the left-hand edge. It doesn't matter where you choose to c. It's just got to be somewhere in that interval, okay? And the limit of those where x of I minus 1 is always less than c or equal to c, and c of I is always less than or equal to x of I. So the x of I is the left-hand limit, x of I minus 1 is left, I is the right, c could be either one of those or anything in between. You can't have it outside, anywhere in between or at one of them. And then the delta x is b minus a over n. The length of that interval, x of I minus x of I minus 1, is going to be delta x, and that's b minus a over n. Okay. Find the area of the region bounded by the graph of f of x is equal to x cubed, the x-axis, and the vertical lines x equals 0 and x equal 1. Okay? Now this looks sort of like the parabola we were just doing, but it's not a parabola. If you remember the cubic function, on this side, it goes negative. So thank goodness we didn't go x equal anything negative. Then that would have been a negative value you violate. But as long as you're between x equals 0 and x equal 1, then it's always positive. Not very positive, but it is positive. Okay? And there's your function f equal x cubed. Okay. Is someone sharing a chat, or what is that about? Okay. I don't know. All right. The area of the region bounded by the graph of f, the x-axis, x equal 1, and x equal thing, x equals 0 to x equal 1 is 1/4. Now, they didn't tell you how they got it. They are jumping the gun on you here. Let's see how they got that value. Okay? Begin by noting that f is continuous. Okay, this is example 5. My thing up here is covering that, so I can't see that. I guess y'all can see it, but I can't. Begin by noting that f is continuous and non-negative on the interval 0 to 1. Next, partition the interval from 0 to 1 into n subintervals. The width of each is 1 minus 0, which is 1, divided by n. So there's your delta x, 1 over n. Okay? Now, according to the definition, you can choose any x value on that ith subinterval. Doesn't matter which one. Okay? For this example, let's use the right endpoint. C sub I is equal to 1 over n. I over n. Okay? Because the left-hand endpoint is 0, I, 1, 2, 3, 4, up to whatever. So the right-hand endpoint would start at 1. So 1 over n, 2 over n, 3 over n. Those are your right-hand endpoints. Okay? You just choose that to be the one that you are looking at. Now, so the area is the limit as n approaches infinity of this summation, I equal 1 to n of f of c, where c is I over n, times delta x. Okay? Well, your f is your cubing function. So you're cubing I over n. So that would be I cubed over n cubed. This is 1 over n. So you have an I cubed over n to the fourth. 1 over n to the fourth is going to go on the outside. In fact, it can go outside the limit, in fact. Okay? And you're just left with I cubed. And that's what they show here. The limit as n approaches infinity of summation I equal 1 to n. This is your I over n cubed, and then your delta x is 1 over n. The right-hand endpoint is your I over n, so that's the C1 you're using. Okay? So that gives you the limit as n approaches infinity. Oh, no, you got to stay inside here because n is inside the limit. 1 over n to the fourth times the summation I equal 1 to n of I cubed. But wait a minute. Go back a couple pages, few pages, and see what I cubed is, the summation of I cubed. That was number 4 on page 295, and that was n squared times n plus 1 squared divided by 4. Okay, so that's what we're going to use. The limit as n approaches infinity of 1 over n to the fourth times n squared times n plus 1 squared over 4. Now again, I think I would do this slightly different than I think they're going to do. At this point right here, I would divide this n squared into the fourth. It just gives you 1 over n squared. And then multiply this out. You get n squared plus 2n plus 1 over 4. Okay? Well, take that 1 over 4 out too. Make it 1/4 of all that. Okay? So here's what they've done. Okay. Now, again, they skipped some steps. Do you need to see these steps done for you? Yay or nay? Help me.
Yes.
Yes? Okay. So let's go to the white screen, the whiteboard, or whatever they call it. New share will be the whiteboard. You ready with your marker? Your stylus? Yeah. Who was it? Jalen? Are you ready to go? Okay. I don't hear anything. Jalen, are you ready? If not, I'll go on and start writing. Okay, that'll bring them out of the woodwork. So what we're going to...
It wasn't me with the stylus.
Oh, who was it? Alea? Aaliyah? Was it you?
No.
Who had the stylus? Was it Morgan?
I think it was like Esther or something.
Oh, Esther had it. Esther, are you there? Yeah, I see Esther's name over here. Do you have the stylus? The ionizing pen? Writable screen? Tablets PC? Who had it? Well, nobody claims it. So I'll start writing, okay? It won't be, it's going to be bad. Okay. I'm going to leave off the limit part now. We'll go back to that. Okay? So what we had after the limit was 1 over n to the 4th. Okay, times. That's ugly, but it's there. You had an n squared, because this is your I cubed, times n plus 1 squared. And that was all over 4, if my memory's right, was it? Okay. Now, that's the part that we're trying to reduce. Okay? Now, in my mind, the easiest way is to divide out an n squared here and make this an n squared. Okay? So if it's okay with you, I'm going to get my eraser and change that 4. Oh, I was supposed to pick up an eraser and it didn't. Well, this is another problem with this thing. After a while, it doesn't work anymore. And I don't know why. I can't get the eraser. Okay, so what I'll do, I'm just going to write over it and make it a 2. Just understand that's a 2. I can't get my eraser to work. Okay? So what we're going to do with this then is square this binomial. That's going to be an n squared plus 2n. Y'all know how to square binomials, right? Ooh, that's ugly. Plus 1. Okay? And that's all over 4n squared. Okay? Well, now I'm going to split that term, into each one of these over 4n squared. So the first one's going to be n squared over 4n squared. That's just going to be 1/4. There's your answer right there. Okay? But I'll work out the rest of them. It's 1/4 plus, ooh, ugly. Okay? 2n over 4n squared. Well, the 2 cancel in the 4 twice, and the n will cancel in the n squared n times. So it leaves you just 1 over 2n. Okay, with me so far? Plus, and then the last one is 1 over 4n squared. It's just 1 over 4n squared. Can't do anything with that. Nothing cancels out. That's 1 over 4n squared. Okay, painful, painful, painful. Okay, as n goes to infinity, that goes to 0, that goes to 0. Your answer is 1/4. And that's what they got. So you take the limit as n goes to... Yes.
How did you get the 2n?
Oh, okay. When you square n plus 1, that's the same as n plus 1 times n plus 1, right? That's what it means to square something. Multiply it by itself, right? Yay or nay?
Yes.
Okay, that's what it means to square. Now you FOIL it. N times n is n squared. Okay, now you do the outer. N times 1 is n, so that's a plus n. Now you do the inner. N 1 times n, oops, I said it but I didn't write it, is another plus n. That's where your 2n comes from. And then you do the last, and that gives you plus 1. Okay, again, if I could do this, there's your first, there's your outer FOIL, here's your inner, and there's your last. It's supposed to be a smiley face, but I don't draw well on here. This is where you get your 2n. N plus n is 2n. That's the most fundamental way of doing it. The little rule that you go by, square the first term, n squared, twice the product of the terms, 2n, square the last term plus 1. Okay? It's the same thing as this because you twice the product. Because it says this times this, the outer gives you plus n, the inner gives you plus n. That's 2n. Does that answer your question?
Yes, thank you.
All right, good deal. Good question, by the way. All right, that was example 4. Oh, I'm sorry, 5. Okay? See, this thing's covering my screen. I'm going to clear the screen here. All right, or do y'all need it any longer? That's how you came up with the answer 1/4. Now, let's see if example 6 is going to show back up in our, where's my pen here? Okay, PowerPoint. And why it goes back here, I don't know. Let's see what this one will do. I think it does the same thing. Let's try it. Oh, it does. It goes straight to it. Okay? And that's where they get, you see, all we did was do this part here on the whiteboard, and it came up with this. And then you take the limit as n goes to infinity. Well, that stays 1/4. As n goes to infinity, this goes to 1/2 times a really, 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 really big number. That's going to 0. And 4 times, 1/4 times a really, 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 really big number squared is even a really bigger number. And that's going to 0. So that's why you wind up with a 1/4. Okay? Now, the area of the region is 1/4. Okay. Now, they're skipping examples 6 and 7. My question to you, are you okay with skipping on, or would you like to see them done? Now, here's a feature about example 6. Okay? Example 6, you can go to larsoncalculus.com. You don't have to own the book. You don't have to have a code. You don't need anything. Just go to larsoncalculus.com and you'll see a worked out example number 6 worked out completely. But I'll be glad to do it if you want me to do that. Okay? Example 7 doesn't have that, but we can still do it if you'd like. What is your pleasure? Do 6 and 7? Neither? Both? Either? I don't care.
Can we do both?
Do both, okay? So, let me go to the whiteboard. You asked for it, you got it, Toyota, okay? Okay, here's the whiteboard. Here's example 6. Find the area of the region bounded by the graph of f of x is equal to, I get a little better of this with time, but not much. Still slow as molasses. Equal to 4 minus x squared. 4 minus x squared. Okay. Now, what we're finding, the area of the region bounded by the graph of f of x equal 4 minus x squared, the x-axis, and the vertical lines x equal 1 and x equal 2. Okay? Now let's just, for the fun of it, figure out what it is when x is equal to 1. This would be 4 minus 1 squared is 1. 4 minus 1 is 3. That's positive. We're good with that one. When you do x equal 2, that would be 4 minus 2 squared is 4. That's 0. Well, guess what? It's not negative yet, so you can do that. So you're going from the place where the graph is 3 to the place where the graph is 0. Okay? So it's positive everywhere in between that. And they do show you the graph in the text, and I will show you that graph, if I can get it Is that it? I think no, that's not it. Oh, there it is. There it is. Okay, you probably can't hear me well because I'm behind the book, but there's the graph of 4 minus x squared. And you see it's positive everywhere there, and you're going from 1 to 2. Okay? From 1 to 2. All right. You got the idea of the problem then, right? Now, the question is, where do you want your C on this one? Well, let's see. We got several questions. Let me hit them as they go. Number one, when I showed you that function, it's continuous. Always positive, okay? It was doing like this, okay? So it's always positive and continuous between 1 and 2, okay? It's never negative. It went to 0, but didn't go negative. So begin by partitioning the interval into n sub-intervals, okay? Well, it's from 1 to 2, so the difference, 2 minus 1 is 1 divided by n, so your delta x is equal to 1 over n. It seems to be one of their favorite ones, but it's pretty easy to work with. Okay, it looks like there's some more chatting going on, which is fine with me, but if I need to respond, let me know, and I'll do the same. Okay? Now, they say, where are we going to choose our C sub I? Well, they like that right endpoint, and I sort of do too, because if you use the C sub I to be the right endpoint, just like we saw before, this is C sub I, that's always going to be I over n, okay? No, I'm sorry, it's 1 plus I over n, because the other one started at 0, this one starts at 1, so it's going to be 1 plus I over n. That's an I there over n. Because you're starting at x equal 1, and then that's a pretty ugly looking n, isn't it? Still not very good, but let me see if I can make it look a little more like an n. Okay. You're starting at 1, and then every interval after that is another I over n. 1 plus 1 over n, 1 plus 2 over n, plus 1 plus 3 over n, 1 plus 4 over n. Those are going to be your intervals, your right-hand ends. Okay? Now, what you want next is to do, this is sort of jumping the gun, but it's okay. The limit, this is ultimately what you're looking for, the limit as n goes to infinity, because you're going to start with whatever, this is a pretty ugly infinity. Hey, it didn't come out as bad as I thought it would. Of your summation when I is equal to 1 going to n, that's usually what your summation will be, of your f, now this is the maximum value, okay, f is C sub I, that's going to be the height times your delta x, which is your width of that rectangle. That's not a very good delta. That's a little bit better. Delta x. Okay. That's what you're looking for. That's your limit rule here. Goodness gracious, I'm tired of holding that book. Okay? Now, if it's okay with you, I'm going to not write the limit over and over and over again. I'm just going to do the summations here. Okay, the f of c, remember this, here's your f. So the f of c is, I'm going to leave off the summation for now too. Let's just deal with this. F of c is 4 minus x squared. Okay, only that's going to be a c sub I. But your c sub I is 1 plus I over n. So that will be, the f of c sub I is going to be 4 plus, and your c, okay, I'm sorry, 4 minus, looking at the wrong direction. Oh no, is my eraser going to work now? Nope. I can't get the eraser to work. Okay, so forget this. This is a minus sign. Minus. Okay, 4 minus, and then your c sub I is 1 plus I over n squared. That's your c sub I. Okay, and all this is multiplied by delta x, which is 1 over n. That's an ugly n. But understand, remember, that's an n. Okay. Now, the summation sign went before this, and the limit went before that. Okay? It just takes me so long to write them, I'm trying to avoid doing that. Okay. So, let's first multiply this. Just like we did before, it's 1 squared, which is 1. So I'm going to write this down, 4 minus, open parentheses, 1. That's 1 squared. Then twice the product of the 2, that would be 2I over n. So plus 2I over n plus the second one squared, I squared over n squared. Okay, and then we're going to have all that multiplied by 1 over n. Now, oh man, I have a sort of a pinched nerve, and it makes it really awkward to sit this long. That's why I love teaching. I stand most of the time. I can't stand here, so that's why I'm wiggling around like a, see, I had a friend from Spain, he called it move around like a chickpea in the mouth of an old man who had no teeth. You know, you can't chew it, it just moves around. Never mind, that's really bad. Never mind. All right, now, I should have gotten rid of this before. This 1 over n can go outside here because we're not using it. I'm tired of writing it. So it goes outside here. It's inside the limit, but it's outside the summation. So that 1 over n should be out there. Okay, let's do the part here. This would be 4 minus 1. Let me not even write that. Ooh, I've already written it, haven't I? Let's make that a 3. Because you see it's 4 minus 1 is 3. Minus 2 over n times I minus I squared. I should have said 1 over n squared times I squared. Okay. Okay. I already pulled the 1 over n on the outside. So that's what we've got here. This is inside the summation. So maybe I should write the summation there. I won't write the rest of it, the I equal 1 to n, but you understand that part. Okay, Well, this part, we know what that goes out to. This becomes 3n. Summation of I equal 1 to n of 3 is 3 plus 3 plus 3 plus 3 plus 3 plus 3 plus 3, which is 3 times n times. Okay? Now, this will be a minus 2 over n, which has nothing to do with the summation. Okay? And then you're going to have times the summation of I. We know what the summation of I is. That's n times n plus 1 over 2. I sure hope it is, because I can't erase anymore. Okay, remember that? Minus, I'm going to pull my 1 over n squared on the outside. Okay, and then what we have here is the summation of I squared. Well, y'all remember what that one is too, don't you? That's n times n plus 1 times 2n plus 1. I don't memorize these things. I just write them down so much I can't help but remember them. 2n plus 1. But you'd always need to check me and make sure I remembered it right. Okay? And that's over 6 if my memory's right. Okay, so that's all the stuff that is inside. Now, leaving all this stuff out makes it really tough to remember. The 1 over n is inside the limit, but outside this. This is what was just the summation part. Okay? So, let's see what we can do with this. The good news here is this 2 and that 2 will cancel out, and this n and that n will cancel out. One of these n's will cancel that n. Okay, now let's see what we've got left. This is 3n. That was the easy part. Okay, now minus an n squared plus n over 4. Because we couldn't do anything with the 4 if my memory's right. Okay? I hope that's a 4. Was it? Or is that an n? No, that wasn't a 4. Sorry about that. Yuck. That was an n that I crossed out. Sorry about that. Okay, so let's make this a minus sign here. Minus n squared minus n. Because all those denominators went away. And here we still have a denominator, so let's not forget that. This is 1 over... In fact, let's do it this way. Let's multiply those two together, and you get a 2n squared okay, that's this times that, and then you have a plus n plus 2n, so that's plus 3n. We've seen that before. And then you have a plus 1. And that's all over 6n squared. No, 6n. That's an ugly 6, isn't it? Okay, don't say anything. Okay. Now, let's see what we've got here. 3n minus n, that will be a 2n. Minus n squared. Okay, and then you're going to have all this mess. Okay. Well, to get this over the same denominator, we're going to have to multiply this term by 6n, and then everything will be over 6n. Okay? Now this gets to be messy. I don't have much room to mess. So let me try it up here. I'm liable to lose some things here. So if you multiply this denominator 6n by that numerator 2m minus n squared, I believe that's going to be 12n squared minus 6n cubed okay, minus I'm sorry, 2n squared and then you're going to have a minus 3n and then you're going to have a minus 1. And all this is now over 6n. Okay. Now, if I'm reading this right, that becomes a 10n squared, because 12n squared minus 2n squared is 10n squared, minus 6n cubed that's supposed to be a 3. I can't get it to move there. That's supposed to be a 3. Minus 3n. That 3 did a lot better. Not well, okay, minus 1. All that over 6n. Okay, that's a 2, that's a 3, that's a 1. Okay, not written in great form, but it's there. Okay, that's everything that was inside the summation. Outside that, remember we had another 1 over n. So I'm just going to make this an n squared here now, because we pulled this 1 over n outside the summation. All right, I've got a problem, I'm pretty sure. I've got a cubed in the numerator, and I don't have a squared in the denominator. That's not good at all. I've dropped a power somewhere. Okay? This 1 over n came out front. And, oh, okay. Between my writing, my scratching out, my not being able to erase, I've lost the power somewhere. But the point here, and this is the one that's giving me problems. I don't know where I blew it. But if you do these two, 10n squared over 6n squared, that gives you 5/3. And that is your answer. And I'm sorry I botched it up, but it's all this mess of having to write with my pen, with my fingertip, and that's, I have sticky fingers and a sticky slide, and it's a terrible way to try to write. But that part comes out right. 5/3, that's your answer. I don't know how I messed up this term so badly. Somehow I did. And I can't see right now how I did that. I think I just misread something. But I can't see it now. So anyway, the 5/3 is correct. Follow it in the book and go to your larsoncalculus.com. I think you'll see how it works. How are we doing on time? We go until we got another hour, right? Yeah. Correct? Yeah. All right. Rather than go back and try to find and undo or just redo the whole problem, let's go on to example 7. So I'm going to clear the screen here. Sorry about that. I lost a power there somewhere. Okay? I don't know where to find it. This time we're going to do example 7 is a region bounded by the y-axis. Okay? Now, so I'll write it down for you here. A little bit not used to doing it this way. Here we have a f of y. Your function is a function of the vertical axis, not the horizontal axis. That's supposed to be a y there. It's a pretty ugly one. F of y is equal to y squared. So basically this is your x, and x is f of y, and that f of y is y squared. And the y-axis, and this is for an area between 0 and 1 in y. And when y is equal to 0, this is 0. When y is equal to 1, this is 1. So it's positive everywhere, positive y value everywhere between 0 and 1. Okay? Now, rather than trying to draw the picture, let me show it to you. There it is. Okay? It basically, if you did it like that, it's your good old parabola that we're used to before. But this is with the y-axis. Okay? Now, what it looks like on x, if you take the square root of both sides, the left-hand side would become a square root of x, the right-hand side would be y. Y is equal to the square root of x. And that is a square root function, right up there. Okay? But we're interested between the y-axis and the function. So we're doing as a function of y, not as a function of x. Okay? Now, how we usually begin this, okay, first it's a continuous function. F of y is y squared. That's continuous everywhere, polynomial function. It's positive everywhere, but specifically where we're looking, between 0 and 1. And we start off by doing our delta y, because you're going up the y-axis here, you have a delta y, not a delta x, and that delta y is going to be 1 minus 0, which is 1, divided by n. That's your delta y. Pretty ugly n. Okay? Now, what are you going to let your, I guess you want to call it c sub I. Do they still call it that? Yeah, c sub I. What would that be? Well, you could either use the right endpoint. You don't have to. You could use any place. But usually, say right. The lower endpoint or the upper endpoint, because your bars, your rectangles are going like this. So the lower one's here, the upper one's there. The first one's going to be, that would be an I minus 1, okay? And to keep from doing the minus 1, let's use the upper one. So that's just going to be I over n. It's going to be 0 plus I over n, because you're starting at y equals 0, so 0 plus I over n. So this is just going to be I over n. That's your c sub I. Okay? The first one's going to be 1 over n, second one 2 over n, 3 over n, 4 over n. Okay, right. Okay. Now, I think I'll write it once and try not to have to write it again. We're going to deal with the limit. as n approaches infinity, pretty ugly infinity, of your summation, that's a pretty ugly summation sign, from I is equal to 1 to n of your, okay, now first place, let's just go on and do it. This 1 over n, that's going to be your delta y, that's going to be the width of the rectangle. There's no I dependence there, so let's bring that to the outside. Can't go outside the limit because the n is what you're counting, so we're going to need it there. So let's get it out there. And then it's just going to be your f of x, okay? Or f of y in this case. And f of y is y squared, so it's f of ci. So that's going to be I squared over n squared. Okay, you know, I think I just realized where I messed the last one up. I forgot to square the denominator, I think is what I did. I can't say that for sure because I can't recreate it in my head, but I think I did that when I did the, I can't remember, but I believe that's where I messed it up. Here I remember to. Okay, now, again, this 1 over I or n squared, it can go out here too. Okay, so let's make that, I'm not going to write the limit down, but it's going to be 1 over n cubed, the n here, the n squared here, so that's your n cubed, and then would come the summation. I'm not going to write that part either, and this is summation of I squared. Well, we know what the summation of I squared is. This is n times n plus 1. I hope I remember this right. Times 2n plus 1. Use them enough, you'll get to know them fairly well. But I always check. I don't ever do this on my own. I always go back and check and make sure I'm not putting a plus where it's a minus, or a 2 where it's a 3, or a 1, or something else, and this is over 6. Okay? That's what the summation of I squared is, that thing. You have a 1 over n cubed here, so I'm going to wipe out one of these and make it as n squared, and wipe out this n right here. Okay? Now that's going to make things a little simpler, because you have now, and I'm going to pull the 6 out with that too, so it's going to be 1 over 6n squared this is a terrible way to teach, okay? Okay, times the product of these two. Well, we've done that enough, hopefully we know it by now. That's 2n squared okay, 2n squared plus 3n plus 1, okay, times this. Now we're going to put all those over that, over the 6n squared, and 2 over 6 is 1 over 3, and that better be your answer. Yes, okay, and the rest of them, it really doesn't matter, but it's going to be a plus 1 over 2n. No, that's a 3 over 2n. No, 1 over 2n, I was right. Okay, that's a 2 and that's an n. That doesn't look like it. Plus 1 over 6n squared. That's a 6. That's an n squared, supposedly. Okay, that came out pretty good. And this is what you take the limit as n goes to infinity. That goes to 0. That goes to 0, and you're left with 1/3. So there is your area of the region. I know that went sort of fast, but was that okay? Any questions? Was there any step that I went through too quickly? And you say, how did you do that? And again, I left off the limits and the summation because they're so... Any questions?
I had a question,
Yes.
but it didn't have to do with the problem you just solved. It had to do with just the homework.
Right.
What was the homework that you assigned?
Okay. This is okay. Are you needing to go real soon?
Yeah, I have to be at work at 2:00.
Oh, okay. So you do need to go pretty soon. Okay. What will I be assigning today? Is that what you're asking, or assigned in the past?
The previous homework.
Okay. Okay. What I'm going to do is make the 5.2 assignment right now. Okay. And okay, remind yourself, or me or somebody, where we started today. We started at the top of page 298. So the first part of this homework assignment that I'm going to do now is from 5.2. From 5.1, it was very similar to what it's going to be in 5.2. Every group of exercises that are similar do at least one of the odd numbers. Now, do you have this book, or have you got another book?
I have the book you recommended.
Oh, the Larson and Edwards Calculus 7th edition, Early
Yes.
Transcendental Functions. Okay, if you have this book, okay, do you see on page 303, exercise set 5.2?
Yes.
Okay, now, as soon as I finish the next slide and the last example, here will be what I'll say your homework is for 5.2. Any of the odds 5 through 9, they're all located, the answers are in the back of the book, and if you can't get the answer in the back of the book, you can go to calcchat.com. There is the website, calcchat.com. You see it at the top of the page there, and there you'll get worked out solutions for those odd number exercises. Okay?
You were covering the microphone with your book.
I know, I'm sorry, I was trying to talk around it. Okay, but you see at the top of the page, see calcchat.com for tutorial help and worked out solutions to the odd number exercises. You see that in that orange box at the top of page 303.
Yes.
Okay, so if you can't get the answers in the back of the book, go to calcchat.com, and there you should be able to work it out. If you don't know why they did it, if it's not sufficient, then you can ask me in class, out of class, email, whatever. So any of the odd number exercises 5 through 9, they're all at CalcChat. They're all in the back. They're all at CalcChat. Number 5 is also at calcview.com. Now on the back cover of the book, I don't know if you can see that. At the bottom it says calcview.com. And again, I know I'm not talking right into the microphone, so hopefully you can hear me. But the back cover, inside cover of the book, calcview.com, is another place. But if you noticed, on the homework exercises, okay, you see the QR code right there? That QR code near those exercises, you can do your phone to the QR code and go straight to that calcview.com. And number 5 is work there. Then do any of the odds 11 through 15. They're all at CalcChat. Do any of the odds 17 to 23. They're all at CalcChat. 21's at CalcView. Do either 25 or 27. They're both at CalcChat. Now, wait a minute. Okay. All right. And that's where I stopped last time. So those I just gave you from 5 to 27, those are ones I assigned last time because we got that far covered on
Which one were they?
On Monday. Yeah. And then
On Monday?
starting today, you can start doing any of the odds 29 through 33. They're all at CalcChat. 33's at CalcView. 35's at CalcChat. 37 or 39 are both at CalcChat, with 39 being at CalcView. 41 or 43 are both at CalcChat. 43's at CalcView. 45's at CalcChat. Any of the odds 47 to 55, they're all at Calc Chat, with 49 being at Calc View. Any of the odds 57 to 61, they're all at Calc Chat, 57's at Calc View. Any of the odds 63 to 67, they're all at Calc Chat, 65's at Calc View. You can explore doing 69 or 71. They should be at Calc Chat. Now, we haven't done that in class yet. I'm going to do that next, but it should be out there on the YouTube video. So now we're getting into the new material. Well, in fact, 63 started the new material, okay, that I'll still get to. 73 should be at Calc Chat. 75 is a true-false. It should be at Calc Chat. 79 sort of a writing exercise. You can look at that if you'd like to. 79, that's 77. 79 is a seating capacity problem. That should be at Calc Chat. Now, we'll probably get into 5.3 today, but we're not going to go so awfully far there. But listen to YouTube video, and you'll find out exactly what I assigned for today. And you can find out, now the YouTube video, did it end before this point last time? I don't remember. The memory has been having problems. I think I solved part of that problem anyway. So anyway, if the YouTube video works, if the Screencast-O-Matic works, you can always go there and get the assignments. That's where I'll make them and record them there. Now, if the memory goes out like it did again, then you won't hear them, but most of the time you will. Did that answer your question okay?
Yeah, and then as far as like, I guess turning in our homework, do we email it to you or something?
Yeah, okay. You don't have to do it all. Pick one problem, or if you're having trouble with a group of problems, pick one you're having trouble with and circle it or note it and say, I can't get this answer. I don't know how they got this answer. Explain it. Then we can either do that in class, or we can do it, you can do it when you contact me during my office hours. Okay, now, how do you send it to me? That was your question. You can either, if you have a way to scan it and send it to me either as an attachment to an email or as an attachment to a message on Blackboard. Okay? If you don't have a scanner and you have a smartphone, you can take a picture with your smartphone. I think that usually does into a JPEG file. You can either attach the JPEG to an email or attach it to a message in Blackboard. Either way, any one of those four ways. I've actually had one student last term who mailed me assignments. You don't have to do that. And you don't have to send me a whole bunch of them, at least one, to let me know you're doing them, you're understanding, or you're doing them and you're not understanding. Just the fact you're doing them, that's all that's going to be credited with in the grade book. So I'd rather know the ones you're having problems with than the ones you're getting right. Okay?
Okay.
All right, good deal. All right, let's move on to example 7. This, for those who do have the book, the top of page 302. Oh, wait, I'm sorry. We just did example 7. Let's go off of this and back to the PowerPoint. And let's see if it'll pick. There it is. All right. This is in the middle part of page 302. In those 3 examples we just did, 5, 6, and 7, C sub I was chosen to be a value that is convenient when calculating the limit. In general, a good value to choose is the midpoint of the interval, somewhere exactly in the midpoint. That would be taking the left-hand point, x sub I minus 1, adding it to the right-hand point, divide by 2. The middle, the average value. That's the midpoint rule. Then the area would be the summation, actually the limit, but it's approximately the summation as I is equal 1 to n of f of that midpoint value times your delta x. Now, frankly to me, the right and n usually works just as easily. I don't know why they're pushing for this now, but you can if you want to. It may get you there a little quicker. But guess what? You're taking a limit. Well, actually, you're not now. They're not saying you're taking a limit. They're just making an approximation. So the midpoint rule will give you a better approximation than left hand or right hand usually. Okay? So let's see if the next slide does that. No, it doesn't. Okay? They don't have that next slide in here, so let's go back to our whiteboard as my...
I have one more question.
Yes, what's the question?
Sorry. So I looked on WebAssign the other day, and it says that you don't have any like assignments current or up to date uploaded on there.
Okay. Now let me go back over that too. Now, I don't know why it says that. Okay, but let me explain what is the deal with WebAssign. Have you used it before? Do you like it?
I have, and it just allows me to see what I got right and got wrong, and like as far as like sometimes I get videos to show how to do a problem.
Exactly.
If I'm not familiar with it.
And that's exactly how the best way to use WebAssign. Now, I've tried teaching with WebAssign before, not actually teaching, but making assignments there. And I wound up, now this was several years ago, so it may have gotten better. Yeah, I wound up spending more time trying to calm students down because they worked and worked and worked, and WebAssign kept telling them they got wrong answers. So they tried something else and tried something else. The problem was they had the right answer to begin with, but they didn't have it in the form that WebAssign was looking for. So it told them it was wrong. So they thought they missed the concept. They didn't. They had the concept perfectly correct. It's just they didn't have it in the form. You see, WebAssign is a computer program. You put an input in, and that's the only thing it recognizes. It can't think and say, oh, but that's just a different form of this. Yeah, that answer is okay. So I spent more time calming students down and tell them, no, you had it right, you just don't have it in the form they're looking for. So after a while, I just quit. And I said, you can do it if you want to. Additional homework exercises to benefit you. That's the purpose of it. Well, along came this thing they're calling Cengage Unlimited. With Cengage Unlimited, they required, or at least they did, they may not now, they required the students to have a WebAssign account in order to access their ebook. So therefore, I had to do WebAssign. So what I did, the guy got in touch with me. I said, look, I'm not going to use it for teaching. You can set it up however you want to. Pick representative questions, do whatever. Assign them all, assign part of them. I don't care. Just give the students a code. So the guy at WebAssign picked these things. I didn't even know he put due dates in or assignment days or whatever. He did whatever he did. Supposedly, there's plenty of examples out there. You can use them anytime you want to. Or is what you're telling me there's no examples out there?
It says that there's no current assignments present right now, uploaded by the teacher.
Oh my. Well, he did not do what he said he did then. He told me he put them out there. I will get back to him. And is that in every section or just certain sections?
It's all the sections. Like, there's not even like any chapter assignments assigned.
Okay, he must have just blown it. Okay, I'll get back to him and ask him why he didn't put some examples out, some assignments out there. Okay, I didn't know that it happened. As I said, I don't use it, but I want it there in case you want to use it. So, sorry about that. I'll try to get that done in the future. And what you're using it for is exactly right. For you to do more practice problems, using the tutorials, using the whatever, looking if it has ways to help you find the answers, fantastic. Frankly, to me, the calcchat.com, larsoncalculus.com, calcview.com, they do the same thing and you don't need a code. But I'll put them out there so you can also use WebAssign as well. Okay? I'll try to get in touch with him. I won't have time today because I teach until 6:15 this evening. And tomorrow I start at 8:30 and go till 1:15. So I have a little bit of time between 1:15 and 5 o'clock. I'll try to get in touch with him then. If you haven't, picked up anything by next week, ask me again. It may be that I forgot to or he may not have gotten back to me. So ask me again Monday. Okay. Thanks for letting me know. All right. Now, any other questions before we move to example 8? Now, for some reason, that box that was always in the way has now grown to be the entire screen. And I don't know why that's the case. But I'm going to try to work the problem here. But it's expanded that box, and I think it's going to block everything I write. I'll see it, but I'm not sure you will. It'll fade in and out, so you'll see it periodically. So here's example 8. Using the midpoint rule with n equal 4. So let's start with that. If I can get my pen here. N is equal to 4. I've never been able to make that box do anything, and now suddenly it's grown so big I can't. It's covering the entire screen. Can you see where I just wrote n equal 4? Now you probably can. Could you see it earlier?
Yes.
Okay, could you see it earlier? Is it fading out now?
I don't think it has the message in the middle. It's just like the outlines.
Okay, so you can still see n equal 4, right?
Right.
Okay, good. I couldn't tell. Okay. So using the midpoint rule with n equal 4 to approximate the area of the region bounded by the graph of f of x is equal to sine x. So here's our function. F of x is equal to sine x. Miserably slow writing. Okay. F of x is equal to sine x. Okay. And the x-axis, that's what we usually use, for the region 0 to pi. Now I'm going to write it this way because it's easier to write. They write 0 is less than or equal to x is less than or equal to pi. I'm just going to write it in interval notation, 0 to pi. Okay, understand that counts the endpoints. Okay, now, why didn't I say 2 pi? Because if you think about the sine function, it's positive from 0 to pi, and then it goes negative from pi to 2 pi. We can't go negative. Remember, we have to stay, the function is continuous and positive, non-negative. Well, 0 to pi, it works. 0 at 0 and pi is positive everywhere in between. Okay? So there is our function. Okay? Now, here is the graph of the function. I'm going to try to draw that just so you can see everything, but that's the graph I'm going to attempt to draw. Okay? Here's the y-axis supposedly. Here's the x-axis supposedly. Here's my best rendition, which is terrible, of the sine curve. Okay? And this is where x equals 0, and this is where x equals pi. And of course, the maximum value here is 1. This is at 1. Okay, everywhere else is somewhere in between. Your n is equal to 4, so that's going to be, right here would be n equal 2, there would be n equal 4. Okay? Now, what they're using is the midpoint rule. So in other words, your rectangle, the rectangles are going to be using these values here. That value for the first rectangle, which will go like this. This value for the next rectangle, which would go like this. This is pretty pathetic drawing. Okay. This value for the next rectangle, which would go, it should be the same as that one. My sine curve is not very pretty. Okay. And then the next one should be the same as what we had before, from here to here, because this would be the midpoint down here. So let's identify our midpoints. Our midpoint, this was pi halves here, of course. Okay. And when you divide pi by 4, this was pi fourths was the first value. And 2 pi fourths is pi halves. And 3 pi fourths was this one. And of course, the last one would be 4 pi fourths, which is pi. Okay, so our midpoints then are at pi eighths, it's a pretty ugly 8, at 3/8 pi, this is excruciating. It's almost like pulling out fingernails. It's terrible. This will be at 5/8 pi. Where is my stylus person? And this one would be at 7/8 pi. Goodness, that's an ugly 8. Okay, it's even worse. Okay, those are our midpoints. That's where we take our values at. Now, what we're doing is approximating. We're not taking it as a limit as n goes to infinity. We're using these endpoints. But you see the advantage here? This one, this rectangle here overestimates here, underestimates here by almost the same amount. This one overestimates here, underestimates here by very close to the same amount. This one underestimates here and overestimates there. You can't tell. That one's drawn really poorly. And this one underestimates here, overestimates here. And that's almost by the same amount. So this should give you a better estimate. Not a value, but estimate. The way we were doing it is fine. So what we do, our summation then, we're not doing a limit, just a summation. And this would be as I is equal to 1 to 4. Your n here is 4. Of sine of x, sine of c sub I times delta x. Okay, already established your delta x is pi fourths, and your c sub I are these values here. Pi eighths, 3 pi eighths, 5 pi eighths, and 7 pi eighths. Okay, so that's what we're adding together. Well, guess what? The pi fourths is times all of them, so we're just going to do the sine of each of these added together. Sine of pi eighths plus sine of 3 pi eighths plus sine of 5 pi eighths plus sine of 7 pi eighths. Add them together. Now, by the way, if you don't already realize this, the sine of pi eighths is exactly the same as the sine of 7 pi eighths. The sine of 3 pi eighths is exactly the same as the sine of 5 pi eighths. If you don't believe me, pull out your handy dandy calculator and see what you get. Okay? Okay. Calculator. Now, to use a phone for a calculator, you need to turn it sideways. I'm sure you know how to do that. What was the one I said? Pi eighths. And there is a pi key on here. And on my phone, I have to enter the argument first and then do the operation. So it's going to be pi divided by 8 equal that number there, and then take the sine of it. And if, oh boy, I think I'm in degree mode. Okay, let's go back and go to radian mode. Okay, and start that process over again. Okay? Pi divided by 8 equal, same thing I got before. Now take the sine of that, and you get 0.3826 blah, 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 blah. Okay? You write that down. 0.3826834, as many digits as you want to do. I would say just 0.3827. That will do. Okay? Now, let's jump over to 7/8 pi. So 7 divided by 8 times pi equal, that's a number more like 2.7. Take the sine of it, 0.38268343, exactly the same number. Let's do the 3/8 pi. 3 divided by 8 times pi equal 1.178 approximately. Take the sine of it, 0.9238 blah, 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 blah. Let's do 5/8 pi. 5 divided by 8 times pi equal, that's 1.96. Take the sine of that, sine of that, sine of that. You get 0.923879 blah, blah, blah. You get the same answer. So that's why I drew these two the same and tried to draw those two the same. So that makes your calculation much easier, because you do the sine of pi eighths, and you would be multiplying that by pi fourths, okay? But then that's going to be the same answer here. So basically, you're multiplying it by pi halves, okay? So let's do that. Let's go. Well, I've got the one up here for 5 pi eighths or whatever, 3 pi eighths here. So let's take that value and multiply it by not pi fourths, 2 times pi fourths, which is pi halves. So multiply it by pi and divide it by 2. And that gives you a 1.45 blah, 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 blah. Let's just leave it there, 1.45. Okay? You want me to write this down? I'll try to. Okay? Where is my... There it is. Okay? Oh, you know what I'm going to do? If I can, I'm going to type it. Yeah, I can't. It won't let me do it. Sorry. Okay, so it's a 1.45. Now, how did I get that? That was this area plus, this area plus that area. Now I'm going to do these two areas. So I go back and do the pi over 8, pi divided by 8 equal, take the sine of it. Yeah, that's giving me my 0.39. We'll round it to 0.39 and multiply that by pi halves. Pi fourths here plus another pi fourths is pi halves. So multiply by pi and divide by 2, and that equals 0.62 approximately. So plus 0.62. Okay, and I'm going to try to add those in my head and see what we come up with. I think that comes up with 2.07. Did y'all do it in your heads as well? 2.07. You know what the actual area under one lobe of a sine curve or cosine curve is? 2. So we're only off by 7 out of 100. Now, I rounded way before they did. They got 2.052. So I had a lot of round off error in mine. They had even less, 2.052. So that's even better than what I wrote down. Okay? I know that went sort of quickly. Do you have any question on it? Do you know what I was doing? Did it make sense? Okay. That finishes 5.2. Now, I just gave the homework exercises in 5.2 to Esther. Did all of you hear that? Do you need it again? Anybody?
I needed it.
Say again?
I need it again.
You need it again. Okay, any of the odds 5 through 9, this is beginning on my page 303. If you've got another book, just find the book that deals with area using integration, okay? Okay? And in mine, any of the odds 5 through 9, the answers are in the back. The worked out solutions are at calcchat.com. Number 5 is also found at calcview.com, even more detailed. Any of the odds 11 through 15, they're all at CalcChat. 17 to 23, they're all at CalcChat. 21's at CalcView. 25 or 27, both at CalcChat. 25's at CalcView. Any of the odds 29 to 33, they're all at CalcChat. 33's at CalcView. 35's at CalcChat. 37 or 39 are both at CalcChat, with 39 being at CalcView. 41 or 43, both at CalcChat. 43's at CalcView. 45's at CalcChat. Any of the odds 47 to 55, they're all at CalcChat. 49's at CalcView. Any of the odds 57 to 61, they're all at CalcChat. 57's at CalcView. 63 to 67, both all at CalcChat. 65's at CalcView. You can explore doing 69 or 71, they're both at CalcChat. Okay? 73 should be at CalcChat. 75 is a true-false. It should be at CalcChat. 77 is a writing exercise. You can do it if you'd like. Whatever, that's up to you. It should have some help at CalcChat. And, 79 should be at CalcChat. All right, now we're moving on to 5.3, and it looks like we've got time, so let's go. However, I'm not sure that I'm not going to need a bladder break. Can y'all catch a quick one? Would you mind? Okay, I'm going to close the screen sharing from this and go back to PowerPoint. I'm hoping I can get there. Okay. Oops. This isn't what I wanted it to do, but I think I can still do it. Okay. Sorry, it's going to take just... Yuck. Okay. It's taking a little while to load. There it comes. Okay. Now I've got to go back into Zoom. And do a new screen share here. There we have it. Can you see my PowerPoint? Yay or nay?
Yes.
Okay. And we'll start from the current slide. And what I'm going to do here is let's take a quick pause here. I just got to run to the restroom. I'll be right back. Okay? All right. Any questions on 5.2? Okay, 5.3 is talking about Riemann sums, which is a new sort of topic, but it builds on what we were just doing, and definite integrals. So we're still in Chapter 5, Integration, and it won't advance until I click on the screen once. Okay, and 5.3 is Riemann sums and definite integrals. Okay? Now, Objectives here are to understand the definition of a Riemann sum. We don't even know what it is yet, though some of you probably do. We'll evaluate a definite integral using limits and geometric formulas, which is sort of the hard way to do it. And then we'll evaluate definite integrals using the properties of definite integrals. That's how you want to do it. Okay? So, first, let's figure out what in the world are Riemann sums. Now, it seems like they're pretty close to what we were doing, and they kind of are. There are some subtle differences here, and this is starting with example 1. Okay? Consider a region bounded by the graph of f of x is equal to the square root of x. Now, this thing right here, you can't see it, but it is definitely in my way. Okay? I'm going to try to get rid of it here. Okay. F of x, square root of x, the x-axis for 0, x between 0 and 1, positive everywhere here. There's a square root function. We've seen that before, hopefully. Okay. It says evaluate the limit as n approaches infinity of the summation of I is equal to 1 to n of L sub c sub I times delta x of I. Yeah, we were doing that before. What's new here? Okay. Now, in this case, they said c sub I is the right endpoint of the partition, and here is the weird partition they use. The partition given by ci is I squared over n squared. Not I over n, but I squared over n squared. Now, why would you think they would do that? Well, guess what? You're taking the square root of your c sub I, and it's real easy to take the square root of I squared over n squared. That's I over n. So really, your partition is not evenly divided like we did before, but they're spaced out. Okay? And that's sort of the difference in what we were doing before. Before, we were just doing even intervals, b minus a over c over n. That was our delta x. Now, these c sub i's, and the c sub I was anywhere in the interval. Now the c sub I is this, which makes for a variable intervals. Okay? These do not have equal width anymore. Okay? The first one's at 1 over n squared. Next one's at 2 squared over n squared, 3 squared over n squared, 4 squared over n squared, 5 squared, up until you get to n minus 1 squared over n squared, and then the last one is n squared over n squared. Okay. You might say, why in the world would you do that? Well, in this problem, it makes it easier. Okay? So the width of the ith interval is I squared over n squared. That's the right-hand n minus I minus 1 squared over n squared. That's the left-hand n. Okay? You're going from I minus 1 to I. Okay? So these, and each of those is given by this weird interval formula, squaring both of them. Okay? Now, if you do the math with that, you'll see this is, of course, I squared. This will be I squared minus 2I plus 1. Okay? When you subtract, the I squared minus I squared goes to 0, and then minus a minus will give you 2I minus 1. That's all that's left in your numerator, all over n squared. So let's see if that's what you get. I squared from here minus, and here's your I squared minus 2I plus 1. When you put the minus in front, it becomes minus I squared plus 2I minus 1. All over n squared. These two I squareds go out, and you're left with 2I minus 1 over n squared. These add to 0, you're left with just this over that. Okay? That's the width of the ith interval. Okay? So different intervals will have different widths because they are your different I values. Okay? Now, so the limit is then as n approaches infinity, and this looks just like before, the summation of I equal 1 to n of alpha c sub I, where you're using the c sub i's from the previous slide. Oh, yuck, I have to go several back. There's your c sub I squared over n squared. Okay, and then your delta x sub I is going to be, where's my cursor? There it is. There's your delta x sub I, right there. Okay, so that will be the limit as I approaches infinity of the summation of I is equal to 1 to n, this is n approaches infinity, of the f of c sub I. F took the square root of your c sub I. So it's the square root of I squared over n squared, which comes out just being I over n. Nice. And then times your delta x of I, which is 2i minus 1 over n squared. Okay? So what does that come out being? The limit, okay, let's back off one. Notice you get an n in the denominator here and n squared here, so that's a total of n cubed in the denominator. That isn't affected by the summation at all, so pull it in between the limit and the summation because it is affected by the limit but not affected by the summation. So pull out the 1 over n cubed there. And that's what they did, 1 over n cubed, and then you're left with that 2i squared minus I. Okay? Now remind yourself where that came from. An I from here and a 2i minus 1 here. When you multiply that, you get 2i squared minus I. Okay? So that's what you get there. Same rules apply from before. The I squared is n times n plus 1 times 2n plus 1 over 6, and I is n times n plus 1 over 2. So plug those in here, and you get the limit as n approaches infinity of 1 over n cubed of 2 times, there's the I squared, minus, there's the I, n times n plus 1 over 2. Okay? Now, my guess, they skip a bunch of steps. Oh boy, there they did it again. All right. Now, am I right to guess that you want to see how they work that out or not? Do you feel confident in working out yourself, or you want to see it? Help me, somebody. You want to see it? I assume so. So let me go on and go back to the whiteboard. Let's see if the whiteboard is straightened up any. No, it hasn't. Okay, at least the yellow box around it isn't there anymore. I don't know if that matters. Okay, now, where did we leave off in the book? Or on the slide set. We had written this part down, so let me try this. 1 over n cubed okay, that's a cube, the 3 there, times 2 times n times n plus 1 times 2n plus 1. Where's my stylus when I need it? Okay. All that's over 6. Okay, and close that parentheses. Okay. Minus, and this was our n times n plus 1 and that's over 2. Okay, and then we'll close the big bracket. Now, again, I want to skip some steps. Let's see if my eraser is back. No, it's not. That part didn't come back. This 2 will certainly go into the 6. That'll go 3 times. Still going to wind up with a... Not going to make any difference in the long run because you're going to have 6 as a common denominator anyway. Now, still, for the life of me, I can't figure out why I can't cancel out one of these n's with this n that I factor out of all that. So I'm going to go on and do it again. It seemed like it messed us up before, but I'm going to do it now. Divide out those 2 and make this a 2. Since I can't erase. Okay? Now, again, what we did here to cancel out the 6, we're going to have to undo it to get least common denominator. Least common denominator between 3 and 2 is 6. So it's going to be 2 times this thing here. And let's go on and multiply that out. We've done it before, and that would be a 2. That's the 2 from here that we're having to go back in. Let's multiply these together, and that's 2n squared. That's an ugly 2. 2n squared. Okay, and then you get plus 3n. We've done this enough, you should know this by heart. Plus 3n. And then you got a plus 1. 2 is times all that, minus 3 times this. So that would be a 3n minus 3. Okay, I'm not putting that in parentheses. And all that is, everything now is over 6. Okay, so to keep from having to write so many things so many different times, this comes up being 4. This is 2 times 2n squared, 4n squared. Okay, and this is 2 times 3n, that would be 6n, minus 3n will be a plus 3n. Okay, that's an ugly n. And here you have a plus 2 minus 3, so that's going to be a minus 1. And all that is over 6 from this denominator, n squared from that denominator. So 6 n squared. Okay. Now, just like before, and remember we're taking the limit as n goes to infinity, the only thing that survives here is 4 over 6, which is 2/3. Okay, because 3n over 6n squared would be 1 over 2n, that goes to 0, minus 1 over 6n squared, that goes to 0. Okay, so we wound up getting the same thing this time with the answer of 2/3. Okay, so I showed you one way to do it. They just skipped and did it. So let's go back to the PowerPoint, which I think is this one. Yes, and that's how we got the limit of, now they kept the powers greater than they needed to, but wound up with the same answer. They got 4n cubed plus 3n squared minus n over 6 over n cubed. And take the limit as n goes to infinity. This goes to 4 over 6, which is 2/3. This goes to 1 over 2n, which goes to 0, as n goes to infinity, and this goes to 1 over 6n squared minus 1 over 6 squared n squared, and that definitely goes to 0. So you're left with 2/3. Okay. Any questions? Well, there they work it out in kind of gory detail, so same thing I just did. Up here, they skip steps like crazy from here to here. I mean, skipping multiple steps. Here, they carry this out in gory detail. I don't know why, but you get your answer of 2/3. There's working it out with a Riemann sum with an unusual choice of your interval. Okay? Now, we know that the region shown in this figure here, we just calculated to be 2/3, and since this is a square of 1 by 1, that's area is 1, that means this area has to be 1/3. Okay? But if you remember back when we did the delta y's, remember? That was exactly this function here, y is equal to x squared, and you did it from 0 to 1, we came up with 1/3. So sure enough, 2/3 plus 1/3 is 1. So that should make you feel nice and warm and fuzzy inside that everything worked out well. Okay? Any questions? Now, because the square bounded by 0 to 1 and x going 0 to 1, y is going 0 to 1, has an area of 1, you can conclude that the area of the region shown here is 2/3, since this region up here was 1/3. So they did it the other way. It doesn't matter that the intervals, subintervals have unequal width. Doesn't matter. It all works out. Okay?
Dr. Fowler,
Yes.
just to let you know, it's
Oh,
10:20.
you already ran over. Thank you so much. I don't know. I guess I could go on forever. It looks like to me this finishes the bottom of page 5.3. Well, we might go back and say that. So we'll do that we'll start at this slide next time. We didn't get enough done to do any new exercises in 5.3, so we'll let it go like that. Y'all okay with that? All right. We'll see you on Monday. Have a good weekend, okay? Any questions? All right. Ending the recording. I've got another class starting in 2 minutes.